All right, we are back for more visualizing quantum circuits we're simulating a quantum computer, we're visualizing quantum circuits, and where we got to yesterday, actually got a little farther afterwards, was visualizing our first kind of complete circuit, and using it to visualize the Fourier transform, which has a bug in it that we want to sort out. And what I did afterwards last time was I just put this legend across the top to kind of help make this legible. But oops, seems like when I alt tab away it exits. So you can see these are just sort of each eighth of the way around the circle, the unit circle, what the color would be. So we can see here this Hadamard gate that's Hadamarding the first the 0th bit. So the 2 to the 0 bit, we could call it, is 3 1s and a -1. Hold on, my cat needs to get out. So we can see this matrix just at a glance is 3 1s and a -1, 3 1s and a -1. And if you think about this in terms of each column hits one basis vector, so the 0th column hits the 0 basis vector, the first column hits the 1 basis vector, and so on. This makes sense. Because this corner up here is basically going to Hadamard 0 and 1 as if it was just a 1 qubit system. And it's going to Hadamard 1, 2, and 3 as though it's just a 1 qubit system. And so that's kind of what you would expect to see here. And likewise, this is a Hadamard gate that hits the first qubit, the 2 to the 1 qubit, so the one on the left, and you can see it's the same matrix, but it has the second and third columns switched, is one way to think about it. So now if you look at the second, it's always ambiguous, so let's just always 0 index everything. So if you look at the 0th column and the second column, you can see it's kind of following the same pattern as one corner over here, where it's Hadamarding the 0, it's Hadamarding the 0 and the 1, or sorry, the 0 and the 2 into each other, and the 1 and the 3 into each other, which makes sense because we are Hadamarding the 2 to the 1 qubit. So this makes sense. This, by the way, is the Fourier transform that we have implemented. And the problem with this is that it's not resulting in the right thing. So the final state here should be we've input the basis qubit, the qubit that always reads 0, 1, which is the qubit that always reads 1 in binary. What we should get from that is 1 I -1 -I, and instead we're getting 1 1 -1 -1. So that's wrong. So we gotta think about why that is. The first thing though, I want to do a slightly better job of rendering complex numbers. So I'm going to create a new function, and I'm going to create a new test, in fact, that tests complex, say pretty print complex, and what do I want? Yeah, I want something like this. I love these. These are great. something like this. And let's just implement that. Pretty print complex. Should take a complex number. And this isn't quite enough, but this gets us started. What happened here? The 0, so 0, yeah, so okay, so if the real number, call this Z, let's see, complex all over the place. If the real number isn't equal to Z and isn't equal to 0, then we're just starting with the real number. What's a format string look like in Rust that will get rid of all decimals? Format string Rust. Let's see here. I think this should just do it. Why are we bothering to say if z.real? We always need that part. And then if imaginary isn't 0, oh, that's why. Because sometimes we just want to display I, but first we need to check if the whole thing is 0. That's fine. Okay, plus 1I. Okay, so we want to get rid of z.in equals 1, result equals format plus I. And what else we got? Oh. What happened there? If it equals 1 and then else if. And okay, and then this case is bad. Let's say let real result and then let me imaginary result. This can just be imaginary format this. If it's 1, then it's I. Otherwise, we don't even need this. And then we'll say, we'll return result at the end, and we'll say, what's going on here? Real result. No, never real result. This can just equal I to string. And then this one just takes the imaginary. And then we say, if real result is blank, then if z dot imaginary is less than 0, we do that. Otherwise, that. Otherwise, we do that. And we can just say let result equal this, and then return it. And z dot imaginary doesn't like me. Oh, it's not a function. Okay. Else if imaginary result is nothing, then we need just real result. Dot imaginary dot absolute value equals 1, then we just want I. There we go. Okay. And now in our draw legend function, we can make the text pretty print complex. And that looks horrible because we're getting way too many decimals. So we need 2 or 3. 2 is probably fine. That's not working. What's the issue here? Complex exponentiate complex I time divided by 8 should should be 0.707 plus 0.707. What happened here? Oh, it's forcing it to always be. Does it have to be 2 dot? Or dot 2. It probably has to be dot 2. But now my worry is that it's going to add decimals where it shouldn't. Oh no, it worked. Oh, no, it didn't. It added decimals where it shouldn't. So I want a Rust format string that gives me decimal precision. Name dot star. So maybe if I put a star after the format, pretty print complex to star. Doesn't like that. Dot star 2, doesn't like that. 1, 2, 3. Rust decimal format string decimals or less. $sign at the end. Fails. So I just round it. Maybe that's the easiest way rather than trying to do this as a format string. Round 2. That's to the 0th. Dot. That at all. 1 bit. Sorry, I should show what I'm looking at. 7, 8. Yeah, this is so. I don't want the decimals unless they're needed. Integer is the precision. Takes an argument. Hey Zeiss, thanks for the follow. How's it going? I'm trying to work out how to use a REST formatting string to get as precise as I need it to be. And I'm not really seeing a format string that'll do it. More broadly, though, what I'm working on today is visualizing visualizing a quantum computer. So let me just get rid of these format strings that aren't working. And I'll show you where we're at the moment. Let's see if this does it. Yeah, okay. So here's where we're at the moment. Is that showing up? Yes. Oops, and then it closed. So this is a quantum circuit down here that's operating on 2 qubits worth of information. So with 2 qubits, you can represent any superposition of 0, 1, 2, 3, or 4 in binary, and then the various gates within the circuit transform the coefficients in front of those binary basis states. And the coefficients they're complex numbers, and they always, if you square them and add them up, you'll always get 1, which corresponds to the probability of the computer is always in some, the probability of the computer being in some state is always 1. And then you can represent the individual gates as matrices. And so really these are just matrices with complex numbers in them. But I'm trying to use colors and the sizes of these boxes to represent the complex numbers to make them scan a little bit easier visually. I'm not sure if this is where we'll wind up. I'm just kind of exploring it for now. But for instance, this circuit is meant to be a Fourier transform, a complex Fourier transform. It's actually not working right. The result isn't ending up at the right number. So hoping to use this visualization to kind of debug what's going on with the Fourier transform. But you can see, for instance, this is a gate that turns a definite state into a blend of that state and the one with its 0th bit flipped. So, for instance, if we start with the 0, 1 basis state, we end with a mix of 0, 0 and 0, 1. And the mix is 50-50, even though these look different. They only differ. One of them, the coefficient is 1, one of them, the coefficient is -1, and so when you square them, they're both going to be 1. It's actually 1 over root 2 in order to make the numbers work out. But I hate the formatting on my legend up here, and so I was trying to get the formatting to work a little bit better. And I think what I'm going to do is just say pretty print real number x and we'll just say not this. We will say let x equals x times 100 times 100 divided by, or we'll round that, and we'll divide by 100, and then we'll format it. We don't need to format it at all if we're doing it this way. And then and then this becomes pretty print real number, and this becomes pretty, whoops, I definitely know how to spell, pretty print real number. Cool. Oh, pretty good, thank you. This looks fun. Yeah, it is fun. It's pretty interesting stuff. I knew a fair amount about quantum mechanics before I started this project, but not that much about quantum computing. And so it's been interesting trying to work it out. Let's see if we got our test passing again. Fails. I lost an I somewhere. Let's see here. So, imaginary result. So I think we just need an I2 string. Oh no, we need this to be format I and that thing. And okay, and the rounding is just off. Let's do 3 digits actually. 3 digits seems sane. If I were being really good, I would render this as e to the I tau over 8, but I'm not going to. And last but not least, computer thinks this should be negative. Do I think this should be negative? If we go 1/8 of the way around the circle, don't I think it should be positive? Feels like that's what I think. Also, it should never say plus, minus like that. So if it's not 0, then if it's 1, we just call it I. If it's positive, then we call it z of imaginary, and then we decide the sign later. That seems a little more like it. This is why we have tests. And getting close. So if the real result is not blank and the imaginary result is not blank, then we do a plus sign or a minus sign accordingly. Why am I getting two minus signs here? Oh, I do need to check whether I just do this as the absolute value. Hey, test passes. Okay. All right, so let's take a look at our quantum Fourier transform and try to work out where we're going wrong. Ooh. Why is this not... Hang on a second. Don't I test for this? Pretty print, complex number. I do, I have tests for this. Did I miss a format string? Draw legend. Pretty print complex. No. I'm confused. My test is passing. Okay, I'm gonna guess that it's because I'm comparing floats, which I shouldn't be doing. So, let's say if z dot absolute value is very close to 0, we'll say if z dot real absolute value is not close to 0, we'll say if imaginary dot absolute value is not close to 0, we'll say still passing. And nope, something's failing. What happened? If... Oh, this is actually meant to be if z dot imaginary is less than 0. This was fine. And this is also fine. Heavy Rain says, hello, it's C# language. No, this is Rust. So Rust is a systems level programming language. So it's operating at the same level as something like C or C++, but it has some really nice features around safety that C++ doesn't have. So basically the compiler enforces practices that mean that you essentially never have to worry about things like memory leaks, trying to allocate memory twice, There's just a whole category of bugs that you can run into in C++ that you don't have to worry about in Rust, and it's very close to being as fast as C++. It is my favorite language. It's just awesome. I can't recommend it highly enough. Cool. Let's see what we got here. All right. Now things are rendering a little bit nicer, and we can take a look at what's going on with our Fourier transform. So, the Fourier transform, and I'm using this book, An Introduction to Quantum Computing by Phillip, Kaye, Raymond, Laflamme, and Michele, Mosca, as my resource here. It's a great book. It's free, and it served me very well so far. So I know that the quantum Fourier transform isn't working right because I have this test. Let's find it. Fourier transform simple, which if I run it, it fails. And it fails because when I run the Fourier transform, this is just a 2-bit Fourier transform. When I run it on the 0 vector, it works correctly. So what it should do is just say, I'm going to go, when I pass in the 0 vector, it says I'm going to go 0 of the way around the circle for each basis vector, and then mix everything together. So I'm going to put a 0 in, and I'm going to get 0 of the way around, which is just 0 out, 1 out, 2 out, 3 out. When you put a 1 into it, it should go 1/4 of the way around the circle for each one. So it should be a mixture between 0 out, 1/4 rotated, so I times the 1 vector, half rotated, so I squared, which is -1, times the 2 vector, and then I cubed, which is -I, times the 3 basis vector. And that's what we're testing for. So there's some rounding junk in here, but this is exactly that state, and what we're getting back is wrong. It's 0.5, 0.5, -0.5, -0.5. So it's not rotated, rotated, which makes no sense. So we want to debug why that is, and we can see in the visualization that that's indeed what's happening. So here's that final state that's wrong. This is not rotated, rotated half. So this is incorrect. So let's go through the logic for what that's about. Heavy Rain says it looks very cool and very hard. I guess so. Thanks. I'm glad it looks cool. It takes a certain amount of perseverance, but the perseverance, I don't know, comes pretty naturally when you've done a bunch of math and coding. I've definitely been struggling with getting this particular quantum Fourier transform to work so far, but I'm pretty confident that we'll be able to get there. So let's break this down. So what this is doing is we're taking the vector with all of its probability on 0, 1, which is the 1 basis state, and we're putting it through a Hadamard gate that blends across the 2 to the 0 qubit, so the rightmost digit. So we get a blend of 0 and 1. And then we're performing a controlled rotation by a quarter, which is I, and that's 3 1s, and then I is a controlled rotation, which does nothing in this case, because we're not, this I only affects the fourth basis vector, and we're not using the fourth basis vector at all. And that seems a little odd to me, so I'm kind of suspicious that this might be where we're going wrong. We Hadamard the other qubit now, so this splits across the leftmost qubit, and then we have to permute the digits. So we need to swap 0, 1, and 1, 0. 0, 0 stays the same, 1, 1 stays the same. And this is the recipe that we were given in the book, I thought. It's not working. So let's find out why. So here we are in the book. Can you see the book? Yes. And here is the full circuit for an arbitrary number of qubits. But for 2 qubits, we would first Hadamard on the first bit. They use indexes starting at 1, which is annoying because they should index everything from 0 because they're mathematicians. I guess maybe they're physicists, I don't know. But mathematicians and computer scientists start at 0. And in my view, that's the correct way to do it. So I have to mentally shift all of these. But okay, they take the 0th basis vector and they Hadamard it. So we're doing that already. They perform a controlled rotation using the second basis vector to control the first basis vector. So here I think is where we've gone wrong, because that's not what we had here. We have 1, 1, 1 I, and what we want is to use the we want to use the leftmost qubit to control the rightmost qubit. And in particular, in this case, what would I expect to happen? We have a blend between 0, 0 and 0, 1. So I would expect the fact that 0, 1... Oh no, this kind of looks right to me, actually. Let's see. Oh hey, Heavy Rain, thanks for the follow. Appreciate it. It's saying we use the second qubit to control a rotation of the first qubit. So that would mean that when the second qubit is 0, I would expect no rotation. And indeed, that's what we're getting, is no rotation. If the first qubit is 0, then the second qubit gets rotated. Is that right? Controlled phase shift gate. We already looked at this. Controlled phase shift gate. Yeah, okay. So this is what it looks like when 0 controls 1. This is what it looks like. I want 1 to control 0. Is it just the same matrix? Is it just the same matrix? Let's think about it. So there's this note in the book that says it doesn't matter. It's symmetric, which I think I believe. Okay, so that's not the issue. We have the matrix that we would expect. Okay. Then, and it's r sub 2, which means it's 2 pi, which is tau. So tau times I over 2 to the k. So this should be 1 over, it should be a rotation by 1 over 2 to the 2, which is 1 over 4. And a rotation by 1 over 4 is I. So, because when you rotate, when you multiply complex numbers, it takes 2 pi or tau of the way around to get back to where you started, and so tau over 4 is I of the way around. Yes. Okay. Let's get our... I don't know why Nanu keeps on... It closes the window when I'm not literally staring at it, which I find a little frustrating. Okay, and this is definitely I. Yes. Okay, and it kind of makes sense that the control rotation doesn't do anything in this context, because the bit that's controlling it, or the bit that's controlling it, well, we said it was symmetric, and the 0 bit would be the controlling bit in that case, and it would be off. So this makes sense. So then the next step in the circuit is to Hadamard the other gate, the other qubit. So it's essentially this one here, which I believe. And then there's this note in the book that says we then need to rearrange the output qubits, which is this. I'm going to get rid of the rearrangement for a moment just to see what we end up with. So in our function where this is our test function, in our function where we create a Fourier transform, we're going to get rid of the permutation gate that we added at the end. And I guess I didn't have to do that. I could already see what the output is. And it doesn't look right. Looks very close to being right, though. The action of the Fourier transform takes the x basis vector and does a mixture of all the basis vectors going x over m, right? So m here is 4, and x is 1. So it should be going a quarter of the way around the circle each time. But that's not what it's doing. It's going halfway around the circle each time. That's where we're not quite right. Here's the 2-gate circuit. We are going the other way. So this is x1 Hadamard, controlled rotation Hadamard, and we get a result. Really seems like that's what we're doing already. They're saying that the result that we get is a mixture between 0 How should I even read this? So, like, this is the 3-qubit gate. This is the 2-qubit gate. I don't entirely understand how to read this when I guess this is saying that that this should be the tensor product. The output is, which is the input here because it's the inverse of what we're doing, but it should be the tensor product of these two things. And I guess I could work out what that is. It's this, and then this times this, and this times this. So if we were to work backwards, like, I don't understand how this can work without this gate applying to this state. Like, transforming that state in some way. Doesn't really make sense to me. Qubit state. The 1-qubit state already works. I have a test that proves that. rotation sub 2 is a 1 over 4. Rotation of 1 over 4. How can it be symmetric? Well, it's symmetric because addition is symmetric, essentially. C-phase gate. Do the global phase difference in the matrix definitions of phase and RZ. They're different gates. Yeah, it's fine. Let's look at controlled gate. Quantum gate. Wikipedia. Controlled gates. The controlled gate in general is this. Phase shift gates. And so obviously, if the diagonals, it's its own inverse. All the algebra, I feel like all the algebra is working out and it's just the final answer that's not. Let's maybe take a look at the inverse quantum Fourier transform, since most of the examples in the book are the inverse. Try that. Visualization. And I want to add a lot more functionality to the visualization, which I'm going to do in a bit if I still am hitting issues. So the inverse QFT is meant to basically just rotate in the other direction. Hang on, this kind of looks right. This kind of looks right. We put in a 1, and we get out something that's been rotated to negative I. No, to negative 1. And then to negative I, and then to I. One over m is a fourth. Oh, so this looks wrong because it hasn't been permuted yet. But if we permuted it, if I put my permutation back, this would be right. Is there a typo in the book? Is that the issue? I'm like very wary of believing that there are typos in published things rather than just I'm doing something wrong in the math. Wait, what just happened? What just happened? Now all of a sudden it's... What just happened? Hang on. Get rid of the permutation. Oh, because the permutation is happening up front. Is the permutation in the wrong place? Is that the issue? The last thing that should happen in the... This would be correct if it was permuted at the end. I think the permutation's in the wrong place. I think that's what the issue is. So if we put this up here instead... Okay, so this is 1, -I, -1i. That's correct for the inverse Fourier transform. Let's take a look at the regular Fourier transform. Yo, there it is. 1i, -1i. I think this is correct. Let's put in the basis state 2. What do we expect to see then? We expect it to go in quarter steps, or in half steps now. So we expect kind of a similar state to last time. Yep, we get 1, -1, 1, -1. And then if we do it in 3, we should get essentially the inverse Fourier transform, which we do. 1, -I, -1i. So good. Okay, let's look at an 8. Let's look at a 3-qubit state. Basis vector 1. Let's see, by the way, I don't know if my visualization is going to handle this nicely. Oh, that's not so bad. We can work with this. We walk off the side. Okay, that's fine. I want to... Well, I guess I can expand this to look at the answer. That doesn't look correct to me. I don't think. It's really hard to tell what's going on, though. But it should be going 1/8 of the way around each time. And that isn't what it looks like it's doing. Okay, let's go back to the... Well, let's go back to the 2D case. Or not the 2D case, but the 2-qubit case. Let's commit this. Oh, let's run our tests too. Okay, so now our 3-dimensional Fourier transform is failing, and our inverse Fourier transform is failing. And our test tensor product expression for phase rotation problem is failing. But that's fewer than we're failing before, so. Get 2-qubit quantum Fourier transform, 2-pass. Now, the weird thing is that this circuit says that it's a circuit for the QFT up to a permutation of the output qubits to reverse their order. And definitely it was being applied to the input qubits. Right? This is the reordering. qubit phase algorithm. Okay, let's do a little more visualization. So one thing I would love to be able to do is drag and zoom, which seems useful but a little tricky to implement. But let's try. So these are the wrong size for starters, and that's because we're using a fixed distance between our gates and our registers. So gate to register delta x needs to vary. Delta x per qubit is what we want, per basis is what we want. And then, so 200 essentially worked well for 4 qubits. So that means it should be like 50, I think. It's fine, we'll just experiment and figure it out. And the point is that this should be multiplied by what? By gate dot NQ length, no, n qubits. This should be 2u size dot power of this as u32. And we're trying to multiply an f32 by a u size, which we don't want. Let's do as f32. Okay. That sort of worked, except it's way too big. Let's do 10. Too small. 12. Too small. 15. Still a little too small. 17. That looks okay. Yeah, that looks pretty good. And how does this look for a 2-qubit circuit? Looks pretty good. Maybe we make it just a little bit bigger. Make yourself crazy doing this sort of thing. Okay. Actually, let's do 17 is good, but let's make this a little bigger. Let's make this like 65. Because really what I want to emphasize is the gate operating Let's make this bigger too. Okay, that looks fine. And let's go back to having 3. Okay, and then it would be awesome to be able to zoom. Awesome to be able to zoom. It'd be awesome to be able to pan. I'm not going to do that right now, though. Okay. So, next question. This is the regular Fourier transform in principle. We are first relabeling the qubits, which move 001 to 100. Which doesn't seem right to me, but okay. Let's say we do that. And then we're Hadamarding. We get a blend. Then we're rotating, which does nothing, but then we rotate. So this should be rotating. So rotating these different colors, yeah, they are. So this should be rotating by 1/4, and it should be rotating the first qubit into the second qubit. The 0th into the first, so I kind of believe that. And then this should be rotating by 1/8, rotating the first into the third. Or controlling the third, like using the third as a control, and rotating by 1/8 on the first. And so it makes sense. This effect makes sense. We have 1 and 1, and it's getting rotated into 1 stays the same because the control qubit isn't doing anything, but 101 gets rotated. Okay. And then we Hadamard 2. That looks right to me. And we do one more rotation. And then we Hadamard again. Where's my other rotation? I should have one more rotation in here that's not here. What's that about? Quantum circuit, Fourier transform. We do the permutation, and then for 0, 1, 2, 3, we apply a partial Fourier transform. And in the partial Fourier transform, when we pass in 3, 1 is the case that we care about. we should get a Hadamard, which we do. And then we should go from 2 to 2 minus 2, which is 0. 2 minus 1, which is 2, rather. No, 3 minus 1, which is 2. So this is 2, and this is 2, and this loop never happens. Okay, so my indexes are off. So what do I want here? I love, by the way, that this is what GitHub thinks any comment should be. If you just put a comment and, like, maybe it's a comment that's next to bad code, I don't know, but GitHub Copilot says, this is a bit of a hack, but it works for now. A thing that I've personally never said, although I have definitely done. Okay, shut up, GitHub. Alright. So, how do we want this to work? If we have 3, 1 here, then we want it to go... stop. Then we want it to go 0... We want it to phase shift qubits, start IDX. Okay, so for n qubits equals 2 equals 1, we just want 1, 1. So that it does nothing. For n qubits equals 2, we want maybe 1 I'll say. We want 1 and then 2 so that it does nothing. For n qubits equals 3, we want 1 through 3, 2 through 3, 3 through 3. And in each case, the phase shift gate should get applied to these -1, right? So in each case, it's getting applied to the start index. So the start index should be the second thing, and then start IDX plus I should be the first thing. So this is correct. And then it should run from start IDX plus 1 just to n qubits, no? Doesn't this just work? And then K is the control bit. So K is just this. Start IDX plus 1. No, plus I. Plus 1. Because these are 0 indexed, not 1 indexed. Oh, off by 1 errors are so hard. So this is going to go, so for a 3 qubit state, this is going to go, we're going to come in here, we're going to say 3 qubits, and it's going to be 0 the first time through. And we're going to go, okay, so 1, 2, needs to be n qubits plus 1. so that we wind up at n qubits. And then K is going to be just I plus 1. Right, because we're walking along these. And so it would just be I. Except that these are 1 indexed and I need a 0 indexed version, so I plus. Oh, my brain hurts. It would just be. Let's do a simple case. I is 0 and qubits is 3. So we go from 1 to 3. And we need it to go. So I is going to be 1 at first. We need it to be 2 at first. Yeah, that looks right. Okay. This looks right to me, and I'm sure it's not. Yeah. Okay. Everything fails. Test for your quantum trivial fails. So let's get that one passing. Always go to your simplest test that's failing first. What? Oh. Quantum Fourier transform trivial. So it's not working because attempted to subtract with overflow. Really? Okay. Add gate. Somehow these are too big. Start IDX plus I. Should just be I, shouldn't it? I is ranging over 1, 2, 3. Should just be I. Right, because we're in this situation. Okay, still everything fails. Still subtraction overflow. Phase shift gate. N qubits. Start IDX. seems like this is right. Let's just walk through it. What just happened? Partial Fourier transform. Trivial Fourier transform debug. Partial Fourier transform. Okay. So n qubits is 1, start IDX is 0. So what do we expect here? We expect it to go through the loop once. Or no, 0 times. We expect it to go through 0 times, right? We add a gate. Start IDX plus 1. N qubits plus 1 is wrong. Start IDX plus 1. N qubits plus 1 is going to go through, is going to take n qubits, which is not what we want, right? We don't want it to go through this loop at all. So do we want it to start at start IDX, or do we want it to start at start IDX plus 1? We want it to start at start IDX, I think. So this should just be n qubits. Still a boatload of failures, but the failures are... Oh, no. Okay, we're back to this. Cool. We're back to this. And if we cargo run... Okay, now we have a new rotation in here, and I can't see what happens at the end. So that seems like it worked, and we kind of know that the 2x2 case works. Visualization 2, 2. Let's just check it. One I negative 1. Okay, good. Good. Okay. All right. So now we need to be able to like zoom around and zoom in and zoom out, which is admittedly going to be tricky. So what's the easiest way to do this? Right now we map all of our x, y's. We just pass a bunch of x, y vectors around that are used for positions. So what if instead of that, every time we do an x, y, we apply some zoom? That's what we would want to do. Loop on or transform to ensure that rotation gates get applied. Also, I think I left some comments in there, didn't I? So what's the easiest way to zoom? Let's say we have some zoom level of 32. Let's say that we have some update loop that takes the model. How do I get input in Nano? Nano input. API reference. Text IO. Windows keys, mouse, and time. State keys, okay. So in the app, let's say Nano keyboard input. Would love an example. Nano keyboard input example. Keyboard. Model view controller. Functional reactive paradigm. Code, different events, update. So what if I get do app dot app dot keys, state of the keyboard keys. Events. Note down. This is tracked by the Nano app, so issues might occur. Down is the set of keys that's currently pressed. Keys dot down. For each key. Okay, we're making progress. Hey, Sav10 Senna. Thanks for the follow. Appreciate it. How's it going today? So we'll say zoom is at 1.0. And if there's a key up, we will expand the zoom, and if not, we will shrink the zoom. And then basically everywhere we're doing drawing, we need to do some zooming as well, which ought to be interesting. There's probably a nice way to do this. Is everything we draw as a rectangle or text? We could also just pass it into some function that knows how to do the zooming. That's probably the easiest thing to do. Get zoomed xy, xy vector, zoom. And we want to divide by zoom. Yeah, because when things are zoomed in, that means that they'll have a big coefficient, and we want to make them small. Yes, we want to divide by zoom. Okay, and now everywhere that we are drawing, we want to zoom it. Draw to frame. So draw text is now going to be get zoomed. What did I just call it? Get zoomed XY. Legend XY. And zoom. Where do we get zoom from? We're gonna have to pass it in. Ugh. It's a little bit gross. I don't love this. So what if we create a little wrapper class? Draw as a proper draw. So let's create a little wrapper class. Let's say pubstruct, it doesn't need to be public, I guess. Zoomed drawer. That's a thing. For now, let's not have an offset. And then we'll impl it. And rather than having this function, we'll take self by reference. We will, we also it needs to take the zoom, and it needs to take a draw. And now we don't need to give it a zoom, and this becomes self.zoom. And now we just need versions of text, and so self.draw text, color, and XY. And then we do .text.color.xy, but this becomes self.getZoomed XY. And similarly, we have rect, and we do the same thing. Let's call this WH. And now pubzoom, this needs to be a struct. And this needs to take a draw. Doesn't like color. What does color take? It takes an into this crazy thing. Okay. Just copying the what's the problem here? Self.draw. Oh, this doesn't return anything. Or does this? And what's the issue here? The size can't be known. Okay, can I make it borrowed? Is it add dine or is it? Still doesn't like this. And it's not gonna like this because it doesn't know how to allocate it. Okay. That's annoying. Figure out how to deal with that in a moment. Get zoomed at self. What am I missing? My parens must be wrong somewhere here. Okay. Okay, and now everywhere we want to call draw, we just call into this instead. And the only issue is we need to resolve this type. This type issue. I wonder how, like, the rect function does it. Okay, that's fine with me. Is that fine with me? Color C. Sure. So we can call this rect C. Color C. Where C is this. Nice. And then we do the same thing. Color C. Where C is that same thing. Okay, and now anywhere that we type instead. So let's change the zoom level to a zoomed, to the drawer, zoomed drawer. And then what is this indenting I did here? That's a little miserable. And then rather than passing around draw, we pass around ooh, is this gonna work? Zoom drawer, new app.draw. Not sure if I can just pass around an instance of draw like this. Model.drawer dot increase zoom level by this factor, and drawer dot decrease zoom level by this factor. And let's just implement those quickly. Zoom drawer, blah, 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 get zoomed Y. Okay. Pub function, increase zoom level. Mute self. Mount F32. And do that. Pub function, decrease zoom level. And we divide. Okay. So now we just need to stop passing around draws and start passing around model.drawer. Model.drawer. So I'm not typing it a gajillion times. And then these all become zoomed drawer. And this becomes draw.text now takes legend XY. And it takes this color and these go away. Draw coefficient is a zoomed drawer, and draw gate is a zoomed drawer. And this becomes draw rect is color XYWH. So color XYWH. This needs to be vec2 of this. Maybe let's just do some spacing here. Okay, these go away. Similar story here. this and copy it, and then we'll do this as a background color, bounding XY, and this guy. These go away. And then draw coefficient is fine, but it needs to be a zoomed drawer, which now does dot text color and XY. Vec2 of this. These go away. And last but not least, zoomed drawer. I think we can get rid of these safely now. And this becomes color XY and then W. So color, this could just be XY, and then vec2 of this, and these go away, and we're missing a semicolon, and these go away. Okay, let's see if this worked at all. What buttons did I say I had to click? Up and down. Okay. Whoa. Okay, that's super cool looking and not what it's supposed to look like. But it looks really cool. So what's the issue? The issue is that the boxes are not getting scaled properly. I think. The boxes aren't changing their width and their height is the issue. This needs to be WH, this needs to be WH, and this needs to be self.getZoomed XY of this. So the nice thing about doing it this way is that the type system kind of like enforces us doing it properly. Hey, that looks like zooming. Okay, the text gets kind of screwed up is the only thing. Can I scale the font size? Let's see here. I have like dot font size. I sure can. Okay, and how do I know what the default font size is? How do I know what the default font size is? See here, draw returns a draw. On draw, I should be able to say text. I say text, it begins drawing a text. Okay, I would like to look at what a text is. Sorry, I'm looking at this. I want to find crate. I want to search within this. All right, it's at the top. Text. Font size does not tell me. New. Can I look at the code, please? How do I tell what the font size is? Default. What if I just do... Okay, what if I just do... const font size... Is it an F32? New font size U32. But also I can do font size equals sure. And then in here we do self.get zoom self.zoom times default font size. Yeah, I didn't think that was quite gonna do it. As F32, and then we can say as U32, and it'll round. Doesn't like it. Super fair on a couple of fronts. Font size. And it says it's never used. I don't believe you. Oh. Hang on. What is this? 12 is the default font size. Okay, but I might want to change that. Font size as F32 just for the multiplication. And then let's start this at 12. And my terminal is dead. I also need to start wrapping up. What's going on here? Okay, that still looks fine. And if we zoom out, okay, our text is changing in the wrong direction. Really? Our text is changing in the wrong direction. Oh, because we multiplied and we should have divided. All right. And now the only issue is that our font has disappeared entirely. Font size. Zoom. Not what we wanted. Divide by the zoom. And now we have our fonts back. And things look pretty good. Look at that. All right. I'm pretty happy about that. Very cool. We should be able to put in offset next time. Okay, so we got a couple of bugs resolved. Still think there's a bug. Wait, do I? I don't still think there's a bug. Check it out. This is working now. So I guess one of my fixes worked. Oh, that's amazing. Interesting. Let's just look at the other examples. I don't actually know what the fix was that fixed that. That's funny. Let's just look at 2 quickly. Whoops. And that looks correct. It loops twice through the different goes 1/4 around the circle twice. If we do 3, we should get a weird like permutation basically. I want to map this to my scroll wheel really bad. And we do, right? We go red, 1, 2, green, 1, 2, here, 1, 2. Why is it only 2? Oh, we get back to red every 3. Do we? Oh no. No. It's a weird like we don't have colors in our legend for this, I think. Because it's going... No, it should be going 3/8 of the way around, which should be this, 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 and so on. Wonder if that maybe isn't right. Looks weird to me that we're hitting red again so soon, and it doesn't look periodic. So that still looks a little wrong. If we run our tests, where are we at? Yeah, we're still getting some failures. Okay, but we're making progress. Things are looking good. I'm pretty happy with the visualization. Pretty happy Zoom worked. Next time we'll keep at this. Probably add some offsets so that we can like click and drag around. And then hopefully we can get back to Shore's algorithm once we get the Fourier transform working. That'll be the sort of culmination where we start working towards being able to factor large numbers. Well, we won't actually be able to implement factor large numbers because this isn't a quantum computer, but we'll write the algorithm for it. So anyway, I will leave it there. Thanks for watching. Please follow if you haven't already. Helps me out, and I'll see you guys tomorrow at 1 EST. Thanks.